annual conference. This is actually the first live event since 2020. So attendance is going to be a little bit hard to foresee. But welcome to attend our afternoon session. Today we're having our 43rd annual conference celebration, and we're kicking off with the afternoon technical program. My name is William Gao. I'm the chair for the afternoon technical program. So, as I was saying, this is actually our first in-person event since 2020, when COVID-19 started. And apparently we're still not completely over it. So for people who do need masks, we do actually provide some masks out there in the registration tables. So we have put together a pretty strong technical program for this afternoon. We'll be covering 4 current hot topics, such as artificial intelligence, semiconductors, biotechnology, and last but not least, metaverse. Okay. I'm going to give a very short 2 or 3 minute overview about our technical program this afternoon. The first one is related to AI. So almost every field right now is leveraging the power of AI. And AI, coupled with big data, machine learning requires a lot of training, therefore requires a lot of data. And in order to handle the data, of course, you need memories and storage. So our object about memories. By the way, our first speaker, Dr. Thomas Coughlin, he was 2019 IEEE USA president. And he actually will be also running for the presidency for 2023. Understand? So he's president-elect. There's actually 4 members. So we're putting a plug here that if you are IEEE member, so please do vote for Dr. Thomas Coughlin when your vote comes up. Okay, our second talk is related to semiconductors. So everybody is also aware that right now around the world, there's a semiconductor shortage. Okay, so people, actually all car manufacturers are waiting for semiconductors. A lot of consumer electronics are also waiting for that. So this afternoon, we'll have a very outstanding speaker from TSMC, which is the leading semiconductor company these days. He's going to give us their perspective about the current state of semiconductors. Our third topic is biomedical and healthcare. So I think everybody in the room is aware that COVID-19 has really brought down the entire world. So everybody is the top thing on everybody's mind is healthcare. So this afternoon we'll have a seasoned person. By seasoned, we mean 30 to 40 years of experience. He's an entrepreneur and a VC. And he's going to be sharing with us over his past 30 years, his successes, his failures, and most important, the lessons that he took out from all those years of experience. So that session is also going to be a little bit different than the other 3 in the sense that it's not going to be like a presentation with Q&A, but it's actually going to be like an interview format. It's a one-on-one interview, so what we call the fireside chat. Okay. But you're encouraged to also participate and ask questions, especially for people who are entrepreneurs and want to know how to get started their own company. The last but not least talk, everybody is aware that since October of last year, Facebook changed their company name to Meta. So ever since, the metaverse is one of the hottest topics right now that everybody is really looking for speakers and looking for material. Even the metaverse is also a little bit thing that is pretty new. and the definition is still evolving. Okay, so you'll be learning this afternoon from a startup CEO from Intergem. She was also an associate professor at Purdue. So I'm pretty sure that you will enjoy all the talks this afternoon. At this point, what I'm going to do is actually I'm going to turn over the floor to the moderator for this afternoon, Dr. Yansu Lee here. He's going to be running the afternoon sessions. Again, we welcome all of you here, and we hope that you enjoy the program this afternoon.
Thank you, William. Good afternoon, ladies and gentlemen. It is my pleasure to kick off the afternoon session. We have 4 speaker sessions from 1 p.m. to 5 p.m. I'm just going to say a few words about the format and the logistics, then we'll let our first speaker to begin. Each speaker will have 1 hour slot. Their presentation is about 40 to 45 minutes. And we will have time, about 5 to 10 minutes for Q&A session. Our volunteer will hand over the microphone to you if you give a signal. And please stay if you have more questions that we cannot fit within the 1 hour slot, because our speaker will likely to stay for a little bit to discuss. And we do not have official break between each speaker session because we're quite tight schedule. But you're welcome to use the coffee or whatever as you need. And at the end of each speaker session, we will present a appreciation plaque by one of our representing member from CIE and San Francisco Bay Area. So that's all what I have to say about the logistic and format. Now let me introduce our first speaker, Dr. Thomas Coughlin. Dr. Thomas Coughlin. His talk topic is on the memory of artificial intelligence. He is the president of Coughlin Associates in a digital storage analyst, as well as a business and technology consultant. Over the last 40 years in the data storage industry with engineering and management positions at several companies. He's also author of Digital Storage in Consumer Electronics, the Essential Guide. He was the 2019 president of IEEE USA, past chair of the IEEE New Initiatives and Public Visibility Committees, and active in Consumer Electronics Society. He's a fellow of IEEE and is the chair of Consultants Network of Silicon Valley, CNSV. Now, please welcome our first speaker. Thank you very much.
Thank you. Wu An. That's about as much Chinese I'm going to get out today, but thank you very much for the opportunity to come and talk. It's interesting, this is 2 years later from when we originally were going to do this, so it's a pleasure to be able to come here and to see you people in person. And today I'm going to talk to you about changes in digital storage, digital memory actually, ecosystem, and things that are going to enable the next generation of big data applications, including, for instance, artificial intelligence in data centers, at the network edge, but also in endpoint devices. And this presentation uses a bunch of material from a report that a fellow named Jim Handy and I do on emerging memories. So just to refer to that at the very end. So we're going to first talk about what's going on with memories, why memory is so important in computing and the things we do today, changes in the way that we are doing computing. We'll talk a bit about some of these memory technologies. We'll talk about actual applications in manufacturing of some of these technologies, where the situation is, some real-life applications, an outlook of where we see things go, and finally a summary and some references. So something very interesting is happening in the memory market. Although there have always been numerous alternatives to today's leading memory technologies, metaphorically waiting outside trying to get in, they have never had the opportunity that's been developing recently. Until now, these memories, and there's 4 of them that we're going to talk about today, have been waiting at the door, again, at the metaphorical door. While the market's dominant technologies, dynamic random access memory, DRAM, NAND flash, SRAM, static random access memory, and NOR flash have kept them out because they're made in larger volumes, they have lower prices. Now let's look at why things are changing and why the market has changed in a way that's going to provide opportunities for new technologies to replace some of the entrenched competition, and maybe ultimately leading to the replacement of volatile memory technologies with non-volatile memory technologies that retain their data when the power is off. So data growth is exploding. There's a well-known IDC study that has projected 175 zettabytes of data generated annually by 2025, up from about 59 zettabytes that were generated in 2020, they estimate. And most of this data is going to come from things like sensors, Internet of Things devices that must process that data real time for the most part. For instance, if you have cameras on a car, you're trying to make decisions in the car, so that you need to process that data. And that's going to drive the need to store and process this data in the device or possibly at the network edge if you can deal with the extra latency. Only a small percent of this data will probably be stored long term. Now, the greater use of artificial intelligence in various devices, both endpoint, network edge, and data centers, is also increasing memory requirements. Artificial intelligence, like training, for instance, uses a lot of data in order to be able to train these models. In addition to the growth of data being processed, another important consideration is power consumption, as well as latency, how long it takes to get the data. And also the data rates are important considerations for future system design. If I can get my data faster and I have faster processing power, I can get results faster. And that leads us to look at the memory technologies that can enable handling this big data tsunami that's coming upon us. So memory is a big part of server costs. And it's got to be efficiently utilized in order to get the best total cost of ownership. You can see this figure on the left here. CPUs, memory, and storage have different life cycles, and they probably should be replaced separately if you're going to be effective in doing this. Now, this has driven the use of disaggregation of the parts of a computer in data centers, for example, and creating pools of these resources. And there's technologies in memory, for instance, like CXL, in storage with NVMe over Fabric, for example, that are enabling that. CXL with DRAM possibly merging non-volatile memory technologies is going to be one of the important characteristics in some of these new computing environments. In addition, data access and on-chip data movement in general, it's extremely costly. It takes time to move data around, for instance, a conventional von Neumann computer architecture. And uses energy consumption. It also takes extra time. So you can see this figure to the right. In these kind of architectures, it causes the system and data center designers to rethinking the way that they're use data, possibly, more likely to try to process data locally and to minimize the movement of data, both to reduce power consumption and also to get results faster. So the semiconductor industry is being forced to change the kind of memory technologies that are being used in embedded devices, another important part of the market actually for all these different applications, like microprocessors, ASICs, and other system on chips. And that's because flash memory can't scale to keep pace with CMOS logic process advances, particularly NOR flash, where all the code storage is. Now, this scaling limit was a problem with NAND flash. Planar NAND stopped scaling at about 15 nanometers, and that's when they adopted a 3D structure to continue to provide the Moore's Law type cost reductions and increase in storage capacities. System on chips use NOR flash. NOR flash stopped scaling at about 28 nanometers with the adoption of the FinFET. Some sort of new memory technology is going to be required to support future chips with smaller lithographies, code storage requirements. And that's providing an opportunity for some other technology to replace NOR flash for all processes below 28 nanometers. But it's not just NOR that is heading for replacement. System on chips use SRAM to store temporary data. And this SRAM is poised to stop scaling, or at least slow dramatically. It seems around 14 nanometers. So there's going to be side benefits of changing in memory technologies. Alternative memories not only scale past the limits of some of these established technologies, making them in the long run cheaper to produce, but they are persistent and they have more balanced read and write speeds. Many people know that NAND flash, for example, and flash in general, lots slower writes than reads, for example. And that's going to impact the way systems and software are configured. Now, we're going to discuss these presentations, some of these issues here. But first, let's take a look at what's causing these changes. This is a chart that illustrates the idea of scaling. It shows two lines. One represents NOR flash, that'd be the red line there, and the black line is some new emerging memory technology. Process shrinks and be able to reduce cost for the entire history of the semiconductor market. The process nodes run along the bottom. You can see there that's a different lithography, and effectively from left to right is following history, moving to the right to get smaller lithographies. Flash relative cost is on the vertical axis here, and it's always been declining in proportion to each process shrink. That is, until you reach a limit on how far you can shrink things. And flash memory has a problem, NOR flash in particular, after 28 nanometers. And this is the memory that is used in almost every device for storing code to be able to operate a lot of system on chips. And so that causes cost declines to cease, so it effectively goes horizontal at that point. You don't get any more cost declines, as that red line shows. Now, manufacturers address these issues by looking at new memories and migrating to new memory technologies, which can allow further cost reductions. These memory technologies are represented by that black line that continues to go down on the chart, goes from left to right. Although today they're more costly than NOR flash, because they continue to shrink and get smaller, and I can make more of these on a wafer for a roughly given cost to manufacture a wafer, their cost is going to eventually fall below that of flash, since they can scale past that 28 nanometers. Now, SRAM has static random access memory, has a similar problem. Its scaling slows down or seems to slow down or stop around 14 nanometers. And this is a similar chart that plots the cell area for SRAM chips presented at a major IEEE conference over the past few years. The cell area, which is proportional to cost, is measured on the vertical axis, and the process geometry runs along the horizontal axis, similar to that last chart. The cell area has been shrinking to keep pace with this process, but it abruptly stopped shrinking at about 48 nanometers, it appears. In addition, SRAM is much larger than persistent memory candidates. Generally, SRAM uses 6 transistors per memory cell, so it's pretty large structure. This leveling off makes SRAM another reasonable candidate to be replaced by some alternative memory technology. The emerging memory will increase the wafer cost over that of a standard CMOS logic wafer, because you can make SRAM in a standard CMOS process, but the die size for some chips are going to be smaller, thanks to the fact that this emerging memory technology has a smaller cell area and consumes a much smaller space on the wafer than the SRAM. And so that's going to reduce the cost of these chips, making the design based on these emerging memories more economical than its SRAM-based counterpart. And you'll see some examples of how this is happening in just a little bit here. And that's going to drive future chips to migrate to an emerging memory as an alternative to SRAM. Now, DRAM is the working memory in almost all electronic devices, from consumer to industry and enterprise applications. Like many semiconductor technologies, it has become more difficult to continue the pace of lithographic shrinks and increasing transistor density than it was in past decades. This figure shows the slowing of DRAM scaling, especially since 2007. Although there are variations in supply and demand that cause the prices to go up and down here, there is seems to be a general trend on the cost and price of DRAM. DRAM price scaling in dollars per gigabyte declined by about 37% annually for 37 years until about 2007. So from 2008 on, it's declined by about, roughly, with fluctuations up and down depending on supply, about 8% annually. Now, to show what some of these things mean in terms of not being able to shrink the process to chip size and cost, I'm going to present an animated graphic. So, let's see, there we go. So this is a photograph of an Intel processor chip made on a 45 nanometer process. You can see two very different parts of this layout. The less regular part of the chip at the top is the logic, and the lower half with its very regular patterns is the SRAM used for the on-chip caches. In the past, the entire chip would scale with process shrinks, as is illustrated here. Now, as the process moved from node to node, from 45 to 32 to 22, and finally to 14 nanometers on the right side, the die area and cost would be about half that of the prior generation. It followed a nice scaling curve. Now, we'll use that same chip again, keeping in mind that the top half is logic, which will scale in proportion to the process, and the bottom half is static RAM, which will scale less aggressively. You can see in this series that the top half of the chip gets pretty small towards the end, but it only accounts for about 20% of the total die area for that 14 nanometer process node on the far right. Yet the SRAM, because the SRAM doesn't scale anymore, and that results in a much larger chip than you'd have otherwise. In fact, the die size trend starts to level off at the end. This black line only indicates the height, but you've also got the total, what you're really interested in is the total area of the chip, and that's roughly equivalent to the square of this figure. That indicates a significant difference between the scaling we saw before and the lack of scaling in this figure. And that causes the chip to be larger, and it opens up an opportunity for new memory technologies that allow you to continue that scaling. Now, microprocessors of various sorts are used in applications from data centers to wearable devices. Memory, for instance, NOR flash and SRAM, can be a considerable part of the total die space of a microprocessor. And as we saw on a prior slide, they're also a significant part of the total cost of making these chips. If the memory doesn't scale with the lithography on the rest of the chip, it could take even more space and thus make the chip more expensive. This is driving demand for emerging memories that can continue to scale and can provide these smaller processes. Now, the acceptance of an emerging memory technology depends on its pricing. To capture a mainstream market, a memory must be cost competitive against established technologies. This cost structure can only be achieved through high volume shipments, high volume manufacturing and shipments. Products that don't reach this volume end up playing in niche markets because they have higher prices, so they don't become mainstream. A good example of this is Intel's 3D crosspoint memory. This chart represents, this is a chart from Jim, computing memory storage hierarchy, one way to represent it. For a memory, a storage technology makes sense in this hierarchy where we're looking at the bandwidth, that is the speed of these processes in the vertical axis, and the price per gigabyte on the horizontal axis. It must be cheaper than the next fastest technology on the horizontal axis and faster than the next cheaper technology on the vertical axis. Now, to get 3D crosspoint adopted in this memory hierarchy, Intel had to overcome a chicken and egg problem. The 3D crosspoint must be cheap to sell in volume. 3D crosspoint must sell in volume to get cheap. That's a chicken and egg problem. The same problem stands in the way of other emerging memories. Acceptance. NOR's hard stop at 28 nanometer, and if SRAM scaling does stop around 14 nanometer, opens the door for other technologies eventually to become cheaper to manufacture and hopefully then grow in volume and become mainstream. So these changes are going to cause computing to change, since all these emerging memory technologies are non-volatile. And that brings persistence not only closer to the processor, but if we look in the future, it could eventually bring persistence into the processor itself. Caches, registers, potentially, if some of these technologies become more mainstream, could become non-volatile, and therefore you could turn the power off and they're still there. But that's not right around the corner. So let's talk about today and the near future. So this is an animated slide. It shows a typical data processing system with a processor talking to storage through some communication channel, most likely the network. So how does the data move in this system? So the processor requests data. This is quick and simple. The data is sent to the processor. The processor processes the data, and then data is moved back into storage. Now, moving the data from storage to the processor and back again, numbers 2 and 4 in the sequence, consumes a lot of time and energy. How can data movement be accelerated? Well, let's take another look here. So here's that same system we've just saw, but now some of the processing power we've moved into the storage device or memory device. With this approach, the 4 steps in the earlier diagram boil down to just 2. First, the processor initiates a process by sending a very brief command to the computational storage device here. The data is processed in place in the storage device, and there's no costly data movement as a consequence of that. You minimize the amount of data you're moving around and the time it takes to process that data. So those are some of the things that are going on here that are going to be important. Now, many chip makers have been considering approach of computing in memory, for instance, for some time. And there's devices out there. We've got a list of some of these here. This kind of chip is also often called compute in memory or processing in memory, or PIM, P-I-M. Some of the more prominent examples are here. Micron's Automata dates back more than a decade, as does Venray's Tommy. And all these add a relatively weak processor to a standard DRAM chip. So they can do some processing, but some people go a little bit further. GSI gives every single memory bit its own processing element, for example. That's blazingly fast for a narrow class of AI algorithms. So some of these things have advantages for particular types of thing. Samsung is making noise since last summer about its AquaBolt XL, which is very similar to a standard high bandwidth memory or HBM, like those that surround higher performance NVIDIA GPUs, for example. This insert photo shows one of the hybrid DRAM compute die within the AquaBolt XL there. SK Hynix is working on a chip that they didn't reveal much about, but presumably it's doing similar PIM type activities. And there's many, many other firms working on neural network chips, for example, that mimic the human brain. And we'll look a little bit more about how these work in a few more slides. So the goal of all these is to reduce, again, data movement by adding processing elements into an inexpensive memory array. So that's one approach. Another approach is computational memory. So it's similar. Put some processing into an SSD, or at least bring it closer, so that the data doesn't have to make that costly round trip to the server or to the CPU. All the companies listed here do this, and probably some that we have left off in addition. As was the case with the last slide, the goal again is to reduce data movement by adding processing elements to inexpensive storage elements. Some companies like Inspur, Cohesity, and IBM devote that computation to a single task, like data compression or video compression, for example. Samsung's Smart SSD uses a Xilinx FPGA and enables customizable processing, including encryption, decryption, and virtual data optimization. While NGD and ScaleFlux, another couple of companies there, put a general purpose processor right inside the SSD. Another company called Iditacom puts a processor right beside the SSD or in an array, so it's in part connected near to the solid-state drives, but not within the SSD itself. So there's a group called SNIA, the Storage Networking Industry Association. They've been working on standards in these areas. They've done a lot of work, again, to establish these standards to be able to facilitate the adoption of these approaches. This slide shows 2 of the 4 categories of computational storage that the Computational Storage Task Work Group has defined. A computational storage drive on the left-hand side, which is an SSD with a processor, and a similar drive that allows the host to either communicate with the processor or to go directly to the data. Now this slide shows the other 2 device types. A computational storage processor that manages storage in other drives, that's on the left-hand side, and a computational storage array, which has a number of other SSDs or computational storage devices shown across the bottom there, and the array control that may perform computation on its own. So what benefits can be achieved through the use of these computational storage, or similarly with processing in memory? ScaleFlux made a good argument for this in the use of such devices at the Flash Memory Summit in 2018. This graph shows the throughput of a server performing a fuzzy search. The x-axis shows how many storage devices are tied to that server. The y-axis tells the throughput of the system. The red line along the bottom shows how a certain server would perform when attached to a growing number of standard SSDs. The performance remains roughly the same whether it's tied to one SSD or 8 or 18 or 24 because it's gated by the capability of the external processor. The system is either compute bound or I/O bound in that case. It doesn't accelerate as the storage is added. But if you have some computational capability in the storage devices, the SSDs here, then the computation basically can increase with the number of these devices that are added to it. That black line shows that the throughput scales linearly in proportion, in this case, to the number of computational storage devices that are tied to the host server. Even with only a single computational storage device, the throughput here is shown as 3 times as much as a server can do alone. And that's simply because of the fact that the data doesn't have to travel again back and forth to the host, along with the fact that there are now 2 processors doing some of the job that was previously done only by the server. So what's most important, though, is that the performance increases in direct proportion to the number of computational storage devices that are tied to the host. And again, it's for something that you have the capability in these devices to process. If you want better throughput, simply add more of these devices. So that's a compelling argument, but there's a lot of groundwork that has to be done so that people can start to enable things like this. And that's where standards organizations play a role. Now, one of the things that's also been work that's been done in the SNIA group, and now is developing software that can support this. We'll look here at system hardware and software to enable these new architectures. Development, for instance, of the NVMe, which is now used in most modern SSDs, enables new ways to access data for processing. NVMe over Fabric and extends this model across the network. Remote direct memory access, for example, and other approaches to memory like data access are possible, and emerging fast persistent memories could enable new computing connection modes as well as greater efficiency. Now, there's a lot of excitement, and I mentioned it before, about using emerging memory in standard computing systems. Not only is that emerging memory attractive as a new layer in the memory storage hierarchy, but it also provides a path to making architectural innovations in the way we do computing. In particular, innovations that solve data motion issues, such as occur in a von Neumann computer, where we have spent a lot of time and energy moving data back and forth, is a big opportunity. These energy and time issues can be alleviated by moving from a von Neumann type traditional compute architecture, as is illustrated on the left, okay, to a memory-centric approach like illustrated on the right. And that opportunity has led to new protocols like OpenCAPI and CXL. Such approaches support memory disaggregation by removing some memory from behind the processor. And memory pooling and sharing is also possible to more efficiently use memory storage to address new problem classes, and also, especially in data centers, to more efficiently utilize resources. And heterogeneous computing is another thing that's on the roll here, which allows data to be processed by a variety of type of accelerators. Note that the memory-centric system includes a DRAM that's connected directly to the CPU, might say that's near memory, and a far memory, which would be this CXL pool at the center of the diagram. It's labeled here as SCM, which stands for a storage class memory, which is another term people give to this. Since that far memory, the storage class memory, is shared, its data path to the CPU must be arbitrated, and this adds latency, for instance, with CXL environment, and that's why we call that direct connected memory near and this memory far. The industry is slowly converging on a preferred mix of these solutions to alleviate today's and tomorrow's problems. Now, CXL is backed by a big consortium and will be a standard switch memory ARC channel that enables pooling of non-heterogeneous memory, various types of memory operating at different speeds, which is difficult with DDR, for example. Different latencies, different data rates. In storage boxes or in large installations. CXL supports memory and accelerators for this resource pooling and allocation. The DDR channels continue to be used for low latency memory, at least through DDR5. And what happens beyond DDR5, maybe higher data rates may drive the use of more other types of interfaces rather than parallel memory interfaces. So for memory, the industry appears to be moving towards a specific mix. It's depending on whether the memory is near or the far memory. CXL is gaining popularity for pooling heterogeneous memory or memory with mixed latencies and data rates, and the memory on accelerator cards within a box. Gen Z is now part of CXL, but it was likely to be used to connect storage boxes and racks together. This near memory, the ones directly connected to the processor, has three options in the running. One is the traditional DDR channels, which is used in mobile devices as well as computers and servers. That'll continue to be used for smaller near-memory systems, at least through DDR5. High bandwidth memory, HBM, provides more bandwidth than DDR, but it's less flexible and it's more costly. Oh, there's another one called the Open Memory Interface, or OMI. It's currently used by IBM's Power processors and certain FPGAs. Let's have a look at these three just near-memory interfaces to see how they compare against each other. So this chart illustrates the operating spaces of these three near-memory interfaces. DDR4 and 5, high bandwidth memory, and this open memory interface. DDR provides a satisfactory solution for near memory in PCs and smartphones, for example, but it falls short for high-end servers and accelerator cards. The amount of bandwidth you can get out of it has limitations. Many accelerator cards today use high bandwidth memory for its high bandwidth, especially if they can operate in limited memory space that's afforded by HBM. HBMs are stacks of DRAM chips that present about 1,000 to 2,000 parallel signal paths to the processor from the memory. They can improve performance, but the processor and the high bandwidth memory must be very intimately connected. HBM is used in applications that accept its significantly higher price in return for its blazing speed, for instance in GPUs. Although HBM is a help, it's considerably more expensive than standard DRAM and is available in stacks of no more than 12 chips at this time, limiting its use to lower quality memory arrays. The open memory interface uses existing high-speed serial signal PHYs with a custom protocol to connect the processor to DIMMs. These DIMMs, actually differential DIMMs, are made of standard low-cost DDR DRAMs and an OMI transceiver chip. They can provide near HBM bandwidth at a DDR-like capacity and price. So these are some of these interesting options there. Now, another thing that's going on right now is a concept called chiplets, which is breaking down traditional semiconductor devices into discrete parts and then putting it back together again. There's a new standard that was announced about a month and a half ago called UCIe, which is Universal Chiplet Interface Express. It's a new standard for connecting 2D, that is these planar distribution of chips together, and 2.5D, where you got some stacking, chiplets and system-on-chip packages. Its uses range from system-on-chips for handheld devices to high-end servers. The UCIe standard permits mixing and matching dies from multiple sources with different packaging options. It's a standard, so you can mix and match. Combined with CXL and through a UCIe retimer allows extending off package to connect with other media, optics, electrical, or microwave to access memory, storage, and processing pools. Going to 3D integration, often called heterogeneous integration, that is where we're actually stacking chips one on top of the other, would create stacks of interacting chips providing even denser compute packages with less data movement and lower interfaces. That's a bit beyond what UCIe is doing, but it's the next step. So, we talked a bit about the architectures, about some of the things that are enabling new ways to build computing. Let's look at some of and how the memories are playing an important role in that. Let's look at some of the non-volatile memories that I believe will help remake the ways we do computing. There are many emerging memory types vying to replace NOR flash. All of them share the same attributes. They all have a small single element bit cell that promises a scale smaller than current technologies to support small and inexpensive die and 3D stacking. They also promise to be easier to use than flash memory, that's NOR flash, by supporting write in place with no need for a block erase, and they have more symmetrical read and write speeds. Finally, they're all non-volatile, they're persistent. Data doesn't disappear when power is lost. They can all be used as persistent memory. These new memories are necessary for Moore's law type scaling to continue. They include ferroelectric RAM, magnetic RAM, resistive RAM, and phase change memories, such as Intel's Optane memory. So let's talk a little bit briefly about each one of these. So MRAM is shipping, but it's relatively low volumes today. Everspin is a public company that shipped the most. They said they shipped over 120 million MRAM and MRAM type devices. The company has a partnership with Global Foundries. They're building 300 millimeter wafers for Everspin, and also they're offering MRAM to their customers as a form of internal memory in a system on chip. We'll show some of that a little bit here. We've listed some high-profile applications for Everspin's MRAMs. Another company, Renesas, is shipping an MRAM chip that is inherited through its acquisition of IDT. Other foundries are offering MRAM options to their SoC clients, including Global Foundries, TSMC, Intel, and Samsung, for example. Phase change memory is another technology that's shipping in volume. The most widely known of these is the 3D crosspoint memory developed by Micron and Intel, which Intel sells under the name of Optane. And they sell both solid-state drives as well as DIMMs. It's actually based on technologies that Intel was in development on for over 50 years. Their first Optane SSDs shipped in 2017. The DIMMs shipped at the end of the following year. They're being used in storage system and computer applications. In addition to that technology, ST Microelectronics produces a phase change memory-based microcontroller for automotive applications as well. Resistive RAM is the third technology we talk about. It's also in production, but it's a pretty quiet way. It's been shipping by Adesto, now part of Dialog Semiconductor, since 2013. They've licensed their CB RAM memory technology to Global Foundries, offering as an embedded non-volatile memory option on its 22FDX platform. ARM announced a spin out of Surfy Labs about a year and a half ago, I think it was, to develop and license new types of non-volatile memories based on correlated electron materials in a joint development product with Symmetrics. Other companies currently ship resistive RAM into both commercial and military aerospace applications, and leading foundries are supporting resistive RAM as another alternative to embedded NOR flash. Now, finally, we come to the oldest emerging memory technology, ferroelectric memory, or FRAM. Surprisingly enough, this technology predates the development of the integrated circuit. The photo on the slide was published by Bell Labs in 1955. It shows a single SBT crystal with vertical and horizontal metal traces that could be used as a non-volatile memory. From the perspective of unit shipments, ferroelectric RAM has also shipped more than any other emerging memory technology, in fact, all of them combined, having found its way into over 4 billion chips. It is most commonly used in RFID cards because thanks to its extraordinary low write energy requirements. Until recently, ferroelectric RAMs are based on unfriendly materials like lead and bismuth that most fab managers didn't want to put into their process. But in 2011, a ferroelectric form of hafnium oxide was discovered, and hafnium oxide is very commonly used as a high-K dielectric in semiconductor devices. So there's potentially a lot of promise in people doing research on using this ferroelectric hafnium oxide for its own memory, but also even to extend the capabilities of DRAMs, for example. So let's look now who's making these emerging memory technologies. So leading foundries, those with processes finer than 28 nanometers, are offering these technologies to their customers. They include, again, TSMC, Samsung, Global Foundries, Intel, and UMC. They're offering, for instance, spin tunnel torque MRAM today, and they plan to offer spin orbit torque, which is a faster, lower energy MRAM, and other MRAM technologies in the future. The goal right now is to replace that NOR flash, but some of these faster technologies may also be used for some SRAM replacement. Other companies are offering resistive RAM and ferroelectric RAM. Now here's a Global Foundries roadmap where they're showing a 22 nanometer eMRAM F as a replacement for embedded flash. They also show on here a 14 nanometer SRAM possible replacement for some time in the future. So the 14 nanometer node, 22 nanometer and 14 nanometer node, the 14 nanometer was supposed to be the MRAM S requirement, that is replace static RAM. TSMC, the largest semiconductor fab in the world, is offering eMRAM, as they refer to it, NE resistive RAM, as low density configuration memory starting at the 22 nanometer node. At a 16 nanometer node, they've said they're developing an MRAM product that again could replace SRAM in system on chips. High endurance non-volatile memory is going to allow, again, less data movement, support higher performance, and provide more memory on a given chip size, especially versus big static RAM devices with 6 transistors. So let's look quickly at some applications already using these. So IBM's Flash Core module, which is the basis of their flash-based storage array systems, they were introduced in 2019. They're used in the company's flash system family of products. They're available storage capacities now up to 38 terabytes. They use MRAM chips for write caching, journaling, logs, and data buffering. It uses QLC memory for the flash memory. Use the MRAM cache to reduce the write wear on the flash memory. And these products are said to have twice the endurance of standard NVMe MRAM. So they've shipped over 200,000 of these Flash Core modules with a total storage capacity of hundreds of petabytes. They also have some processing capability, and they've included RISC-V capability processor in these chips that could be used for future programmable sort of computational storage applications. Now, this is a block diagram of a company called Ambix, 4th generation Apollo system on chip. It's both an application processor and a coprocessor for ultra-low power battery-operated IoT endpoint devices. For instance, there's a Fitbit that uses one of these. If you look at the lower left corner, you see the system memory subsystem. It's made up of MRAM and SRAM. The chip pairs a 2 megabyte MRAM with a 1 megabyte SRAM here. Another device is from a company called Newman. It's basically for space applications. They're looking for deep neural network processing in space for a device, be able to do, you're away from things, you need to be able to make a decision, so it helps the spacecraft to make decisions. MRAM is being used in Sony's GPS receiver, which was found in Huawei's GT2 smartwatch, which is built on Samsung's 28 nanometer FDSOI process, includes 8 megabytes of embedded MRAM. There's many other emerging memory devices that ship in production today. They include an MRAM microcontroller from NXP, phase change memory-based microcontroller from ST Microelectronics, and FRAM-based microcontrollers from Texas Instruments and Fujitsu. So another unusual approach that uses some of these memories is some configuration of neural networks. And they're made essentially out of chips that are configured as a memory arrays. And this idea has been around for a very long time. Like almost, and this again has applications in machine learning. These are designed to mimic the way that we believe the brain works. They use a lot of matrix algebra, multiplying inputs by weighting factors and summing the resulting values. This upper graphic on the right-hand side illustrates a matrix of weight of these weighting functions, with the colors highlighting the values in the squares. Higher values are greener, lower values are more red. The lower graphic is an illustration of the inner workings of a neural network chip, the matrix algebra is the reason that GPUs have become popular in AI systems. The attraction of a neural network chip, it may be slower, but the thing is it can perform a huge number of operations all at once. And so for some AI applications, this could be very interesting. And some of these emerging memories are critical elements in some approaches to making these chips. So let's look at some of the applications already using these emerging memory technologies. So let's see, I think this may be an earlier version that I was cutting this out because it's going to take too much time. Let me get out of here. Sorry. Yeah, this is the earlier one. So just to sort of wrap up here, with all these devices coming online, so what is the output for the market? What is the outlook for the market? And that's, so Jim and I we do this report, an annual report on emerging memory technologies, and these are some of the things we talk about. So this chart came from our most recent report. We're working on the new version now for this. The report is called "The Emerging Memories Take Off." It shows that the total emerging memory market, represented here by MRAM and 3D XPoint, could exceed $44 billion by 2031. This chart shows how petabyte shipment growth could drive that number. Compares current projected capacity shipments for the next 10 years for various non-volatile memory technologies, here represented by MRAM and 3D XPoint, versus DRAM and NAND, which are high-volume conventional memories. The assumptions are that 3D XPoint is adopted widely by Intel customers and Xeon servers. Embedded MRAM replaces most system-on-chip NOR and SRAM, and that MRAM has strong appeal for artificial intelligence applications. So the MRAM includes both standalone as well as embedded memory technologies. And just to wrap up here, so what I've tried to show here is that some of the conventional technologies, NOR flash and SRAM, basically seem to be limited in scaling, and even DRAM scaling is slowed. And new volatile memory technologies could fill this void, and particularly offer the possibility of replacing volatile memories, which lose their data when the power is turned off, with non-volatile memories, which don't require refresh and which retain their memory even when the power is off. And that's going to lead to new memory. Also, this is an important part of creating new memory-centric computer architectures, which will be used in artificial intelligence and other data-intensive applications. So storage memory hierarchy, as a consequence, is going to change. It's gradually moving, and we can gradually see this persistence even moving inside of processors themselves, I think, in the long run, as these technologies become more mature. And there are 4 leading candidates for these technologies right now: MRAM, phase change memory, resistive RAM, and also ferroelectric RAM. Leading foundries are offering these products to their customers. They're in use today. There's products out there now that are using some of these technologies. And again, we project significant growth in this market for these non-volatile memories going forward. So with that, there's just more on the report here. If you're interested in taking a look at it, there's some links at the bottom here, some references, and I want to thank you very much, and I could take some questions now. Yeah.
Before we take questions, we'd like to ask our Vice President Jonathan, also the conference chair today, to present the appreciation plaque to our speaker. Please raise your hand.
Yeah. So the big problem with radiation resistance is generally with the charge devices like DRAM, NAND flash, things like that are trying to retain a charge because the radiation can cause damaging of the elements and they can lose their memory. So there's a number of these that are better for radiation hard. The MRAM is one. Ferroelectric memory is also good. Resistive maybe, they don't do charge, they're resistive based, they're not charge based, and so those generally are tend to be better on the radiation side. You bet. Yes.
Yeah, for the in one of the slides, you say the trend is moving from the von Neumann to memory-centric architecture. Maybe I missed the detail there, but look to me, it's even the memory-centric, it still looks like far away from the computational processes. I don't know how does that diagram help reduce the moving data.
Yeah, if the CPUs have been slowing down in terms of the performance gains they've got. People have started to use accelerators. They call them accelerators. They're specialized processors for different applications. GPUs are example, TPUs, things like that. There also are accelerators that are being built into these devices to do the computation. So CPUs have a certain capability of processing, and you can overwhelm them, and that slows down what you're trying to do. The idea is that if I can offload some of that processing to other devices, then I can get results faster. And then I only need to transfer the results back to the processor, to the CPU, or to the network to get out to other things that are going on. So the idea is to go to a more distributed computing environment. CPUs aren't going to disappear, but there's going to be an awful lot of other options that are supplementing them, for various applications. GPUs, for instance, for graphic processing or a lot of AI applications. But also in devices, we're going to see more and more accelerators used in more and more places to do specialized processing. In some of these storage devices, they do storage. Some of these things are just doing storage-specific things. For instance, in that IBM Flash Core module, they actually have a capability of onboard processing. Will do compression and decompression, so you get effectively higher capacity out of the flash memory than you would otherwise. But it's transparent. But they've got more processing speed in the Flash Core module than even the network or the CPU, and so they can process that very fast. You don't even notice it in terms of the general performance of the device. So there's different reasons why people use this processing, but in general, it's because it's getting hard to do everything on just one CPU, and processors are getting cheaper and more plentiful for other applications. Yeah.
Can you give us a high-level explanation of why SRAM and DRAM is not able to scale, and why couldn't techniques like 3D and die stacking help with scaling or mitigate that problem?
On the DRAM in particular?
DRAM or SRAM, or I don't know. I mean, they're probably different problems, but maybe you can just give us a high-level explanation.
Well, the NOR flash, they have a problem after 28 nanometer. It's just they couldn't find a technology to be able to scale that, and so therefore they're kind of limited. So if you need something smaller than NOR flash, that's where these people would use these technologies. So that's kind of like the first thing. The SRAM looks like it's slowing down or stopping in terms of capability of making it smaller. Plus, it's a big cell. It's got 6 transistors versus single transistors or no transistors for some of these memory technologies. So there's a number of things they're doing that. With DRAM, it's not stopped, but it's slowing. It looks like the rate of shrinking is slowing, and that means that it's the price decreases. A lot of fluctuations depending on supply and demand things, but the overall price declines are going to be not as great, for example.
Yeah, I mean, I understand that they cannot scale, but why couldn't they go 3D just like NAND?
Why can't they go? Oh, there is talk about that on the NAND flash, about going 3D. Another thing is they've actually, some people played with the ferroelectric hafnium oxide on DRAM in order to be able to to increase the retention of data on it. You have to refresh DRAM a lot. So this would give it a little higher persistence. So there are things being done on DRAM. DRAM is the hardest one. And DRAM is one of the highest volume. But, So but there are people talking, and a lot of work going on now on 3D DRAM, which, if that plays out, then that changes the game.
Thank you.
Well, I guess thank you then. Oh,
I have one more. I recall like one of the biggest problems for phase change, like 3D crosspoint, was the power consumption. Do you know if that's being solved? Like, is that being resolved to allow better adoption of the PCM memory?
I missed the first part of that. What was that?
I recall like one of the main challenges for PCM, or for 3D crosspoint, was on the power consumption compared to the other devices. Is that something that's actually being resolved as you see?
Phase change memory. So phase change memory involves changing a crystal into amorphous material and back. It's basically a heating process. So it can requires a bit of energy to be able to do that, right? So, they do as much as they can to minimize that. I'm not sure, what kind of, if there's been major advances in that. It intrinsically uses a certain amount of energy to be able to cause those transitions, though.
Yeah, because from the talk, because I think as all the data is actually, so much data is actually being generated, I think power consumption is going to become a big bottleneck for all the memories that's actually going to happen in the future.
For all these memories.
Right.
And that's in DRAM for instance, DRAM uses a lot of energy because you have to refresh it. It's not just that I have to put energy into this thing all the time to keep the data there. So, it's very attractive, it's very fast, but it also chews up a lot of energy. And that was the idea with the 3D crosspoint is compared to DRAM, it used less energy. And they were offering at a price that was less than DRAM, so I could add more memory capability with close to DRAM with DRAM, so it would supplement the DRAM. I get kind of a tiering architecture there, and effectively I get more memory with close to DRAM performance. That was the basic idea behind it. And we'll remain to be seen, how successful that's going to be.
Thank you.
Great. Thank you very much. Glad I finally got to come here after 2 years.
We'll invite you again.
All right, very good, thanks.